Ever wish you could walk through walls? I mean, what if I told you there are these tiny little particles out there that can actually do something like that?
It does kind of sound like something out of science fiction, doesn't it? But actually, it's a real thing. It's called quantum tunneling.
Yeah.
And it really kind of shakes up how we normally think about the world works.
Yeah, no kidding. I mean, in our normal world, things are solid, right?
Yeah,
Like there are boundaries. You can't just walk through a wall. You throw a ball at it, it's going to bounce right back.
exactly. That's how things work in classical physics. Energy barriers, they kind of tell us what's possible and what's not. It's like if you think of a ball trying to roll over a hill, if it doesn't have enough energy, well, it's just going to stop.
Okay, so then how is the quantum world different?
Well, let's imagine instead of a ball, we've got a wave.
A wave.
Yeah. See, in quantum mechanics, particles, they don't act like solid little balls. Instead, they behave more like waves. They're spread out, and there's a chance they could be in multiple places at once. So instead of hitting a wall and stopping like that ball part of the wave, can actually go right through the barrier.
Whoa, hold on. So it's not that they're breaking through the wall or anything. It's more like they're existing on both sides of it at the same time.
Exactly. That's the whole idea behind quantum tunneling. It's not about finding a hole or digging through. It's about the probability of finding that particle on the other side, even if it doesn't seem to have the energy to get there.
So it's like the barrier, it becomes less like a solid wall and more like this fuzzy area possibilities.
Exactly. And that's where things get really interesting. The particle's wave function, the thing that tells us where it might be, well, it can actually extend into and even past the barrier. And this is where the math comes in. The Schrödinger equation, one of the big ideas in quantum mechanics, it actually predicted this behavior.
Wait, so there's an equation that says particles can basically teleport through walls? That's pretty wild.
Well, it's not exactly teleporting like in the movies, but yeah, the math shows us that there's a non-zero probability that a particle can exist on the other side. And this isn't just some theory either. It's been proven by a ton of experiments.
Okay, yeah, I'm starting to get why this is such a big deal. But if it's all about probability, what affects how likely this tunneling is to happen?
That's a great question. Think of it like trying to jump over a fence. The thinner the fence, the easier it is to get over, right? And it's the same with quantum tunneling. The thinner that barrier is, the higher the chance the particle can tunnel through.
Okay, that makes sense. So a really thick barrier that's like a really tall fence.
Exactly. And just like having more energy helps you clear that fence, a particle with more energy has a better chance of tunneling too.
So thin barrier, high energy equals good chances for tunneling. I got it. But where does this actually happen in the real world? Like besides in some physics lab?
Oh, quantum tunnel, it's happening all around us all the time, even if we can't see it. For example, without quantum tunneling, we wouldn't have things like radioactive decay.
Radioactive decay, what does that have to do with particles going through barriers?
Well, think about unstable atomic nuclei. They've got particles trapped inside, like alpha particles. Now, in classical physics, these particles, they shouldn't be able to escape. They just don't have enough energy. But because of tunneling, they've got this tiny chance to slip through the energy barrier that's holding them in. And when they do, that's what we see as radioactive decay.
So this is happening like all the time at the atomic level. That's pretty mind-blowing.
Absolutely. And it's not just that. The whole world of electronics relies on quantum tunneling, too. Those billions of transistors that can fit on a tiny computer chip. That's possible because of tunneling.
Really? I had no idea.
Yeah. It's pretty cool. And things like tunnel diodes, electrons can tunnel through super thin barriers in ways that classical physics just can't explain. This lets us make electronics that are super fast and really tiny, essential for modern technology.
Wow, so our smartphones, computers, all that stuff, it wouldn't be possible without this weird quantum phenomenon.
Not as we know them.
Nope.
And it gets even cooler. We can actually use tunneling to see atoms. There's this tool called the Scanning Tunneling Microscope, or STM.
I think I've heard of that. But how does a microscope use quantum tunneling?
Imagine a super sharp tip, so sharp it ends in just one single atom. And we bring that tip incredibly close to a surface. When it's close enough, electrons can tunnel between that tip and the surface, and that creates a tiny little current.
Okay, I think I'm following you so far.
And by measuring that current, we can actually map out the surface of the sample with atomic resolution. It's like feeling around in the dark. Those changes in the current, they tell us where the individual atoms are and how they're arranged.
So we're not using light or lenses to see atoms. We're using the flow of electrons. That's wild.
It really is an incredible invention. And this ability to see individual atoms, it's completely changed fields like material science and nanotechnology.
This is all super fascinating, but I have to ask, if we can see atoms and even move them around with this STM, is there any chance we could someday use quantum tunneling to do things on a bigger scale? Like, I don't know, walk through walls.
Well, that's a fun thought, but the reality is a bit more complicated. Tunneling, it's statistically significant at the atomic level, really small scales, but when you try to scale that up to something like a human, the chance of tunneling through a wall, it becomes astronomically small. Basically zero.
So no quantum superpowers for us then.
Not in that way, no. But the implications of tunneling at the scales where it does occur, they're pretty mind-blowing. It challenges how we understand reality, and it's led to some amazing technological advancements. And who knows what other mysteries are out there waiting to be discovered.
I mean, we've gone from particles sneaking through barriers to being able to see individual atoms. What's next?
That's what makes this feel so exciting. There's so much more to learn. For example, scientists are exploring how to use quantum tunneling to build even more powerful technologies like quantum computers.
Quantum computers. Now, those sound interesting. Tell me more about those.
Well, imagine a computer that can do calculations way faster than anything we have today. That's the potential of quantum computers. And tunneling could be a key part of making them a reality.
Okay, now I'm definitely intrigued. How would tunneling work in a quantum computer?
So quantum computers, they use qubits, which are like the quantum version of bits in regular computers. And one way to control these qubits to make them do calculations is by controlling how particles tunnel between different energy states. It's still early days, but it's a field with huge potential.
Wow, so we've gone from particles sneaking through barriers to potentially revolutionizing computing. Quantum tunneling really is a game changer.
It really is. And we've only just scratched the surface. There's so much more to explore and discover about this fascinating phenomenon.
Well said. This has been an incredible journey into the world of quantum tunneling. I feel like we've only just begun to explore the possibilities, and I can't wait to see what the future holds for this amazing field.
Me too. The future of quantum tunneling research is incredibly exciting. And as we continue to delve deeper into this remarkable phenomenon, I'm confident that even more groundbreaking applications await us, applications that could transform our world and expand our understanding of the universe.
I completely agree. It's been a privilege to learn alongside you today, and I'm sure our listeners are just as fascinated by this incredible world as I am.
I hope so. And I hope this conversation has inspired them to stay curious and to keep exploring the endless wonders of science and the universe. Because who knows what other mysteries and surprises are out there waiting to be discovered.
Absolutely. To our listeners, thank you for joining us on this deep dive into the mind-bending world of quantum tunneling. We hope you've enjoyed the journey and that you'll continue to explore the wonders of science and the universe. Until next time, keep those minds curious and never stop questioning the world around you.